NASA's 2020 App Development Challenge.
We used C# and Unity as our main coding language and visualized the lunar South Pole using the regional data file.
There were several challenges we encountered during the project. However, working in a team with constant collaboration, we were able to overcome these challenges and create a successful app.
In our initial stage of the competition, we designed a storyboard that we followed when developing our app.
We visualized the height and slope of the moon's surface from a first-person perspective.
To visualize the azimuth angle, elevation angle, and more, we added a dashboard that updates as the astronaut moves.
To make the terrain as natural as possible, we texturized it with a real image of the moon's surface.
In addition to the default terrain, the user can toggle between meshes colored by height, slope, elevation angle, and azimuth angle, using the numbers 1 through 5 on their keyboard. Each terrain has a color key.
Our app is able to find the shortest path between the landing and destination sites that does not exceed 15 degrees of slope and allows the user to toggle between different optimizations, such as the least amount of hill climbing.
We identified 10 checkpoints along the shortest path from the landing site to the destination site. At each checkpoint, the elevation angle to the Earth is greater than the elevation angle to the horizon. Additionally, the checkpoints are optimized with maximum distance between them.
In addition to the required components of our app, we added aspects to our app that enhanced visualization, functionality, and ease of use.
We added stars and the Earth to better reflect what astronauts would see in real life.
A mini-map was included to help the user see their position from an orthographic view and help gauge progress along the path between the landing site and the destination.
Labels were included on top of each checkpoint to easily identify their locations while exploring the terrain.
With the ability to toggle between first and third person perspective, the user can get a better view of the astronaut's location on the terrain.
We also included the functionality to find the shortest path with slope under 15 degrees from any point on the moon to the destination.
The user is also able to change the slope constraint from 15 to 20 degrees, which allows them to compare options for traversing between the landing and destination sites.
We displayed the shortest path from the landing site to the rim of Shackleton crater and determined the minimum slope required to be 17 degrees.
Although our team progressed smoothly for the most part, there were times at which we were stuck. By following the 7 core practices for behavior and ways of thinking outlined in the K-12 computer science framework, we worked together to overcome these obstacles.
When we first incorporated the astronaut, it would fall through the mesh, seeming to not detect it as the ground. We added a mesh filter and a script to detect that filter to resolve this problem.
While using Unity's Pathfinding, we realized that we could only generate navigation meshes on pre-existing objects. Since our mesh was procedurally generated at runtime, we wrote a script to save our mesh as an asset and applied the navigation mesh to it.
One of the biggest challenges we faced was collaborating on this project from 4 different time zones. But through constant communication on Discord, weekly Zoom meetings, and a lot of teamwork, we were able to successfully complete this project without ever meeting in person.
Each of us learned valuable skills, not only limited to coding, but design, team management, and more.
Although none of our team members had ever used C# before, our knowledge of other programming languages helped us quickly learn C# and use it in our app.
We also had to learn Unity from scratch. Through several YouTube tutorials and trial and error, we can now comfortably code using the game engine.
Another skill we learned was how to make astronomy-related calculations such as elevation angle, azimuth angle, and converting between spherical and Cartesian coordinates. This helped us create our dashboard as we needed to make several conversions.
When designing our app, we had to make sure to keep in mind user interface and intuitive controls. For example, we have the WASD keys set to control movement and the numbers 1 through 5 to toggle between meshes.
We received a lot of guidance from our team's lead teacher, a computer science teacher, and our external mentor, a subject expert in geology.
Initially, we weren't sure which platform to work on. Our lead teacher helped us make our decision of using Unity and guided us on how to logically split the project into components.
When creating the mesh, we faced difficulties in transforming the spherical coordinates into coordinates that Unity could understand. Our external mentor gave us a different perspective on the problem, allowing us to think of an alternate solution that worked.
Although we are proud of the progress we made on our project, there's always more that we can improve upon.
A compass would make navigation more user-friendly.
A footprint visual add-on where the astronaut had already walked would make it possible for the user to retrace their steps.
Along with footprints, a walking animation would make the third-person view more realistic.
A rotating Earth would make our simulation more realistic.
To inspire the next generation of space explorers, we presented our app to our school STEM club. Participants learned the basics of Unity, saw a demo of our app, and learned how to join the Artemis Generation Coders.
We also have 2 future community engagement events planned, one at a local elementary school and one at our high school's research colloquium.
To share our work with a wider audience, we created social media accounts on Twitter and Instagram and shared updates about our app, tagging #NASA_ADC in each post.
We want to give a big thank you to NASA for hosting this competition. Our team learned a lot and had a lot of fun creating an app from scratch.